Okay, in this lecture we're going to continue moving through our section 11.4 material on tangent lines and derivatives. So in the first part of this section, we had introduced the slope of the tangent line to a curve at a point as a derivative. It's defined as a limit of some average rate of change of our function, or the limit of the slope of a secant line passing through 2 points on our curve. Now, the value of the derivative, that is the value for the slope of the tangent line to a curve at a point, is a function of x. So in this part of our section, we're going to define the derivative as a function. So before we give that definition, let's think about why we could consider the derivative as a function. So if we have the graph of a function in the xy plane, let's say something of the form y equals f of x, the derivative, which represents the slope of the tangent line to the curve at a given x value, would be the slope of this tangent line to the curve at a particular value, say x equals a. We would have a slope denoted as f prime of a. Now, if we choose a different value of x, let's say that I chose x as equal to, let's call it another value, say b, the point on our curve here would have a tangent line whose slope is something like this. It's a different slope. We would have f prime of b as a different value. So we see that for different points that we're choosing on the graph of our function, the slope of the tangent line to the curve at that point will be different. Therefore, the derivative depends on the value of x that we choose and is therefore a function of x. So let's introduce the definition of the derivative as a function. So here we say the derivative of a function f of x is denoted by f prime of x, and it's defined as the limit as h approaches 0 of the difference quotient f of x plus h minus f of x all over h. So it's the same definition that we had for f prime of a in the first part of this section, but now a, rather than choosing a specific x value, we're just using x. So we're defining the derivative at any value of x, so for any point on the graph of our function. And this derivative is defined in this way, provided that that limit exists. So as long as we're looking at points where the graph of our function does not have a corner, a vertical tangent, or a discontinuity. Now, if this limit does exist, the function f is said to be differentiable. So if the derivative exists, then the function f is called differentiable. And the process of finding the derivative of a function is called differentiation. So a big part of this calculus course will be in differentiation, that is finding the derivative of a given function, and we'll start to see some applications of differentiation a little bit later in the course. So before we look at examples of calculating the derivative of a function, let's introduce some different notation which we can use for a derivative. So if we're considering the graph of a function, let's say y equals f of x, then some different common notations for this derivative of f of x are the following. So the one that we've already been looking at is f prime of x. We use f prime for the derivative of a function. Now, if we're considering the graph of a function, so points of the form y equals f of x, then we could also denote this derivative as y prime instead of f prime of x. We could just say y prime for the derivative. Now, another notation which we could use would be the following. We could say the ratio d over dx of the function f of x. So this is another notation which is used for the derivative of a function. We'll explain this notation in more detail as we move through the course. Or we could also make use of the notation df over dx, or if y is equal to f of x, we could say dy over dx. So these are all different notations which we could use for the derivative of a function. And the notation df dx or dy dx, these sort of last two notations that we were using to denote a derivative, is called the Leibniz notation for a derivative. So let's look at some examples. Now that we've defined formally the derivative as a function, let's look at some examples where we're finding the derivative. So in this first example, we are asked to find the derivative of f of x is equal to 3x plus 2 using the limit definition of the derivative. So if you've taken calculus before, you know some of the rules which we're going to explore a little bit later in this chapter, and you might immediately know that the derivative of this function would be 3. Now, in this example, you are not allowed to use those rules which you might have seen in a previous calculus course because we haven't explored those yet here. And the problem says that we have to find the derivative using the limit definition of the derivative. So we have to use this definition which was being provided here. So let's see if we can justify that the derivative should be 3. So here, f prime of x is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. So in this example, we have the limit as h approaches 0 of, for our numerator, f of x plus h is given by 3 times x plus h plus 2. And then we're subtracting f of x, which is 3x plus 2. And the whole thing is being divided by h. So we have the limit as h approaches 0 of, if we simplify in the numerator, distributing our 3, we have 3x plus 3h plus 2 minus 3x minus 2 all over h. So in the numerator, we see that certain terms will cancel, namely our 3x minus 3x and 2 minus 2 cancel. And I'm left with the limit as h approaches 0 of 3h divided by h. So I can cancel a factor of h in the numerator and denominator. And I'm left with the limit of a constant 3, which is 3. So here, the derivative of the line 3x plus 2 is 3. Now this makes sense from an intuitive definition if we think about the graph of this function. So our function, f of x, was 3x plus 2, which is a linear function. Now the graph of that linear function would be a line whose slope is positive 3 and whose y-intercept is 2. So the graph of our function, y equals f of x, looks something like this. And for any point that we choose on the graph of this function, the slope of the tangent line to the curve through that point would be the exact same as the slope of the line itself, which is a line of slope 3. So hence, we would expect the derivative to be 3. So using this same sort of intuitive idea, we will make use of the fact moving forward that the derivative of a linear function, that is the derivative of a line, is the slope of that line, in this case 3. All right. So let's look at another one that's a little more complicated. In this next example, we are considering a quadratic function. F of x is 2x squared minus 6x plus 3. Now again, if you've taken calculus before, you might recognize that f prime of x is 4x minus 6 immediately. But here, in the problem statement, we're told that we have to find the derivative using the limit definition of the derivative. So we're not allowed to use some of the rules that we're going to see later in this course. We have to make use of the limit definition here. So, in this example, our derivative, f prime of x, is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. So here we have the limit as h approaches 0 of, the first part of our numerator is f of x plus h. So in this example, we have 2 times x plus h quantity squared minus 6 times x plus h plus 3. And then we're subtracting f of x, which is 2x squared minus 6x plus 3. And remember, we're subtracting that entire quantity. And the whole thing is divided by h. So let's see what we have if we expand and simplify in the numerator. So we have a 2 times, if we expand x plus h squared, we have x squared plus 2xh plus h squared. Distributing the negative 6, we have minus 6x minus 6h plus 3. And then we're still subtracting the 2x squared minus 6x plus 3. And the whole thing is divided by h. So now we have the limit as h approaches 0 of, in the numerator, if we distribute the constant 2, we have 2x squared plus 4xh plus 2h squared minus 6x minus 6h plus 3 minus 2x squared minus 6x plus 3 on the end. The whole thing is still being divided by h. So in the numerator, let's see which terms will cancel. We have 2x, and then we're subtracting 2x, so those terms will cancel. We had a negative 6x, and then we're subtracting a negative 6x, or adding 6x, so those terms will cancel. And lastly, our constants, we had a 3, and then we're subtracting 3. Those terms will cancel. And so we are left with the limit as h approaches 0 of 4xh plus 2h squared minus 6h in the numerator, and the whole thing is being divided by h. So now we have the limit as h approaches 0 of, if we divide each term in the numerator through by h, we have 4x plus 2h to the first minus 6. And in the last part of our problem, we're taking the limit as h approaches 0. So here the only place h appears is this 2h term. As h approaches 0, this 2h term approaches 0. And so we're left with only 4x minus 6 for our derivative here. Now notice that that is exactly the expression that we had found up here. So if you've taken calculus before, you know how to find derivatives more quickly without this limit definition. And if this is your first time taking calculus, in our next few sections, we'll start talking about rules which make finding these derivatives much easier. However, a word of warning for the purposes of your homework or the first exam, if the problem says to find the derivative using the limit definition, you have to solve the problem in this way that we've done here, because we have not yet discussed those rules which make finding the derivative a little easier. So let's consider another one. In this next problem, we are asked for the derivative of the function 2 over x. And in part A, we want the derivative of that function using the limit definition. So again, if you've taken calculus before, you might be able to find the derivative quickly as negative 2 divided by x squared. Now in part A, we're told we have to use the limit definition to find this derivative, so let's see if we can justify that. So we know f prime of x is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. So here we have the limit as h approaches 0, and for notational convenience here, my division by h I'm going to rewrite as multiplication by 1 over h out in front. So here another way that I could write this is the limit as h approaches 0 of 1 over h times my numerator, f of x plus h minus f of x. And for notational convenience, I'm going to make use of that in this example. So here we have the limit as h approaches 0 of 1 over h, and our f of x plus h is given by 2 over x plus h minus f of x, which is 2 over x. So, in order to evaluate this limit inside of the square brackets, I'm going to combine the difference of these two fractions as a single fraction. And to do that, I need to make use of a common denominator. That is, I have to find a common denominator for those two fractions. So a good common denominator here would be the product of the two denominators. That is x plus h times x. Now, in order to have that denominator for my first fraction, I would have to multiply top and bottom through by x. So I would have 2x over x plus h times x. And then I'm subtracting 2 over x. Now to get this denominator, I would have to multiply that fraction on top and bottom by the quantity x plus h. So let's see what this gives us. We have the limit as h approaches 0 of 1 over h times, in our numerator, we have 2x minus, if we distribute, 2x minus 2h, and the whole thing is divided by x plus h times x. So let's see what cancels here. We see in our numerator this positive 2x and negative 2x will cancel. And so we have the limit as h approaches 0 of 1 over h times my numerator, all that I'm left with is negative 2h, and then we're dividing by x plus h times x. So from here, we can see that our h in the numerator will cancel this division by h that we have out in front, and we are left with the limit as h approaches 0 of negative 2 divided by x plus h times x. So in my last step, I'm ready to take the limit as h approaches 0, and the only place that h appears is in this denominator. So as h approaches 0, this term disappears, and we are left with a numerator of negative 2, and then in my denominator, I have x times x, or x squared. So we have, for the derivative, negative 2 over x squared, making use of this limit definition. Now in this example, we also include a second part of the problem, which is to find the equation of the tangent line to the curve y equals f of x at the point where x equals 2, and express our answer in slope-intercept form. So here, we are asked to find the equation of a tangent line, and to find the equation of any line, there's two things that we need to know. The first is a point that the line passes through. So in this example, we are interested in the point where x is equal to 2, and since this is a point that lies on the curve y equals f of x, to find our y value, we're going to plug x equals 2 into the function f of x. So let's start by finding a point on our line. We would say at the point where x is equal to 2, y, since this lies on the graph of our function f of x, would be given by f of 2. Now our function was 2 divided by x, so if x is 2, we have 2 over 2, or 1. So we're looking for a line which passes through the point 2, 1, and another thing that we need to find the equation of a line is the slope of our line. Now, in this example, we are asked for specifically the tangent line, and we know that the slope of the tangent line is the derivative, what we found in part A. So here, at the point on our line, when x is equal to 2, the slope of our tangent line, let's maybe call it m, is given by the derivative f prime, where we're interested in the value when x is equal to 2. So using our result from part A, we found the derivative was negative 2 divided by x squared. So if x is equal to 2, x squared would be 4, and this reduces to a slope of negative 1/2. Now, if we have the slope of a line and a point that the line passes through, we can find the equation of the line making use of point slope form. So the equation of our line is of the form y minus the y coordinate for our point, which we found to be 1, is equal to our slope, which was negative 1/2, times x minus the x coordinate for our point on the line, which was 2. So simplifying a little bit, we have y minus 1 is equal to negative 1/2 x plus 1 when we distribute our negative 1/2. And then solving for y, if we add 1 to both sides, we have negative 1/2 x plus 2. So this would be our tangent line. All right. So let's look at another example. In our next one, we're given the function f of x is the square root of x plus 1. Now, if you've taken calculus before, you might be able to find your derivative as 1 over 2 times the square root of x plus 1. But in part A of this example, we're told that we need to find the derivative using the limit definition of the derivative. So let's see if we can derive this formula for that derivative. So here we have f prime of x is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. So in this example, we have the limit as h approaches 0 of, for our numerator, we have f of x plus h, so that would be the square root of x plus h plus 1, minus f of x, which is the square root of x plus 1. And then the whole thing is being divided by h. So to evaluate this type of limit, we had seen in section 1.1, we could make use of rationalization of the numerator. So if we tried to plug in 0 for h, we end up with an indeterminate limit of the form 0 divided by 0. So we can't evaluate the limit by simply plugging in the given value of h as before, but instead we can rationalize the numerator by multiplying by the square root of x plus h plus 1 plus the square root of x plus 1. So I take the same expression that I had for my numerator, but I change this negative to a positive. And if I multiply the numerator by that quantity, I must also multiply the denominator by that same quantity. All right. So let's see what this buys us. We have the limit as h approaches 0 of. When we expand our numerator, let's see what we're left with. We have the square root of x plus h plus 1 times the square root of x plus h plus 1. So multiplying that square root by itself, we are left with x plus h plus 1. Now when we multiply our outer two terms, the square root of x plus h plus 1 times a positive square root of x plus 1, we have the positive product of those two terms. But then when I multiply the inner two terms, I have the negative of square root x plus 1 times the square root of x plus 1 plus h. So the product of the outer two terms and the inner two terms cancel, and then we're left with negative square root of x plus 1 times positive square root of x plus 1, which gives us negative x plus 1. So simplifying in our numerator, we're left with the following. And then we're dividing by, in the denominator, we had a factor of h, which I was then multiplying by the square root of x plus h plus 1 plus the square root of x plus 1. So this gives us the limit as h approaches 0. And in the numerator, we see that our x minus x will cancel, and 1 minus 1 cancel, and we're left with h, which is then divided by h times the square root of x plus h plus 1 plus the square root of x plus 1. So here, this common factor of h on top and bottom we can cancel, and we are left with the limit as h approaches 0 of 1 over the square root of x plus h plus 1 plus the square root of x plus 1. So in our last step, we're ready to take the limit as h approaches 0. And the only place that h appears is in this single term in our denominator. So if h is approaching 0, that term cancels, and we are left with a numerator of 1 divided by the square root of x plus 1 plus the square root of x plus 1, which is the same as 1 over 2 times the square root of x plus 1. So we have the following value for f prime of x. So here in the case when we start involving square roots, this limit definition of the derivative becomes a little more difficult because we have to use this rationalization technique. Now in part B, we have the same question that we were considering in the previous example, where we are asked to find the equation of the tangent line to the curve y equals f of x at the point where x is equal to 3. So again, there's two things I need for the equation of a line. One is a point on the line. So if I'm given the x-coordinate for the point on our line, which was 3, and I know that this is a point on the graph of our function, y equals f of x, well, y is given by f of my x value, which was 3. So in this case, the square root of 3 plus 1, or square root of 4, which is 2. So I know my line is passing through the point 3, 2, and I need the slope of our tangent line, which is the derivative. So at x equals 3, the slope of our tangent line, which we'll call n, is given by f prime of 3. So using what we found in part A, we found f prime of x is 1 over twice the square root of x plus 1. If we plug in 3 for x, we have 1 over 2 times the square root of 4, which gives us 1/4. So now that I have a point on my line and the slope of that line, we can use point-slope form to find the equation of the line, which would be given by y minus the y-coordinate, which we found to be 2, is equal to m, our slope, which was 1/4, times x minus the x-coordinate for our point on the line, which was 3. So simplifying a little, we have y minus 2 is equal to negative 1/4 x minus 3/4, or if I add 2 to both sides, I have y is 1/4 x, and then 2 is 8/4, minus 3/4 leaves me with a positive 5/4. All right. So in this part of our section, we've considered the derivative as a function. We saw that the slope of the tangent line to a curve depends on what value I'm choosing for x. Therefore, the derivative, which represents the slope of that tangent line to the curve, is a function of x, which is still defined in terms of this limit of a difference quotient. And we've seen several examples of evaluating the derivative of a function and how it can be used to find the equation of a tangent line to a curve.